of infinite impulse response filter for filtering an analog value. And okay, fine. And the second thing will be programming of serial interface for receiving and time information from GPS receiver. Okay, I will switch the camera to the Arduino. Okay. Okay. The can you see the picture from the camera with the analog value of the
Yes, we can see it.
Yes. Okay. I will show you briefly how it's programmed an infinite impulse response filter. And next we will make the serial interface. Okay. The infinite impulse response filter is in the end, at least this kind of low pass filter, it's more simple than finite impulse response, because finite impulse response filter has to has in the memory, for example, the last 100 samples, but infinite impulse response filter is it has only 3 variables in the memory. And how it's calculated. I will make the change in the code, but okay. Unfortunately, I don't have the mouse because I have connected the Arduino and the external camera, so I don't have the port for my mouse. I cannot rename it. So this is previous is actual sample plus 9,999 times previous divided by 10,000. So the actual sample is only 1/10,000th of this formula. The most of the formula, most of this part is the previous value. When I change these numbers, for example, to 99 and 100, or so 9 and 10. For example, when previous will be 0 and actual 100, this will be 100 and this will be 0, because it's, for example, it's empty. And in the beginning, it's 0, this previous. When it's divided by 10, the 100 divided by 10, it's 10. It's written to the previous. When the previous is 10 and the actual is 100, this is the formula. So 100 plus 9 times 10 is this is 90. This is 190, and divided by 10, it's 19. So when the 19 goes to the next step, you should imagine that this it's repeating each microcontroller cycle. When the previous is 19 and the actual 100, the previous is calculated like 100 plus 9 times 19. This is 170. This is 270, and 270 divided by 10, it's 27. So this 27 goes to the next calculation, and so on. It depends on which number are you setting. For example, when you set 9 and 10, I will show you what will happen when I build a solution and program. Now the number is changing very fast. When I change the value at the resistor, it is changing very fast. But when I program the numbers like 9,999 or 99,999, and these two 100,000, now you can see that the value is changing very, very, very slow, because each microcontroller cycle is it's going near to the end value, and it goes by an exponential curve. Like when you have, for example, a resistor and capacitor filter. This looks like I had connected a very large resistor and very high capacity capacitor to this potentiometer, but I have programmed it only in the code. So when I change this to the 0, you will see that it looks like when I had connected a very large capacitor with this discharging. Okay. Now when I change it to a higher voltage, okay. So now you can see how it's how you can implement an infinite impulse response filter to an analog value. Do you understand it?
Yes, yes.
Yes. Okay.
Mm-hmm.
These values are depending on an application. For example, these numbers, like such big numbers, are, for example, good for implementation of filter for fuel tank. When you have in the fuel tank and float, which is moving with a resistor, which is changing its value. When you have, for example, a noise in the wires, and you have, for example, moving liquid in the fuel tank, this kind of filter, it's removing all these disturbing components, but you cannot use it, for example, for throttle position in an engine, because you could change the throttle in a split of second, and this will be in this this example, for the gas throttle position, you should have these numbers lower, for example, like 100 and 101 or so, because you could push a throttle in, for example, in a 0.2 of seconds, and it will be disturbing, because the engine will be very, very slow in dynamics. So this is the example for implementation of the infinite impulse response filter. For example, for filtering in sound, to have only the basses in the sound, you will set these values, for example, to the 9 or to the 5 and 6 or so. Okay. So, do you have some questions according to the digital filtering?
No, it's okay.
No, it's okay. So the basic difference between infinite and finite impulse response is that in the finite impulse response, you have in the memory the last 10 or the last 100 samples. And you are making an average value from these 100 samples, for example. And in the case of infinite impulse response filter, you have in the memory only the last sample and some big number which is containing all the previous values. Okay. Now we will try to make an microcontroller example for serial interface. So the first in the serial interface you have to make it's an it's setting up the serial channel and the baud rate. Now I have to open the data sheet. This is our serial interface. And these are the registers of the serial channel. For example, the first register is containing only the flux. It has near to nothing to set up. The UCSR 0A. And this is the register UCSR 0B. Which is containing which we have to set up. The first we have to do is enabling the receive complete interrupt enable. When we write an 1 to this bit, we are enabling the interrupt when the when it's waiting and received byte in the UDR register for reading. This is transmit complete interrupt enable. We are not transmitting, so we are not using it. This is data register empty interrupt enable. We are not using this function. And this is enabling the receiver. Enabling the receiver makes that you are not using the port number. For example, in our case, it's I think port C or port D0. But we are using this pin of microcontroller for receiving the serial value. So This is interrupt, enabling the interrupt. Receiving and byte. And this is the second one, enabling the receiver. This enables receiver, serial receiver instead of PD0. The next we have to set up is setting the baud rate. Okay, this GPS receiver uses a default baud rate of 9600 baud. In the datasheet, you have examples of baud rate settings. The Arduino has an oscillator frequency at 16 MHz. Arduino Uno, at least. So we have to find an oscillator value of 16 MHz. This is for 16 MHz, and this is our baud rate, 9600. And we are not using the double speed of this serial channel. So which number we have to set to the baud rate register for 16 MHz and 9600. What is our baud rate setting? What is our baud rate setting for now? 9600.
0.2%.
0.2% is error. It's
what did you say?
0.2% is an error by this baud rate setting.
You didn't say error.
103.
Sorry. Okay, sorry.
For 16 MHz. And 9600 baud. The error of the communication will be 0.2%. It's only for our information. Why is there an error? When you are receiving and receiving something through the serial channel, you have, for example, the error, for example, for 11.0592 megahertz, the error is near zero in all these for all these baud rates. This is because this frequency could be divided very easily for all these baud rates with these numbers. But for example, when you have the calculation formula for the baud rate setting, the calculation formula for the baud rate settings for our asynchronous normal mode and not doubling the speed this is our case. When this gives you a whole number, for example 100, the error will be 0. But when this gives you a number, for example 100.5, you cannot give to the baud rate register the 0.5 value. You have to put there only the whole numbers. So this will have an error, for example 0.5%. So this is this depends on the frequency of the microcontroller, the error. Okay, our case it's 103 for the 60 megahertz, and we have 0.2 error. Okay, how we make the, for example, the interrupt for the for receiving and byte on a serial channel. Okay. No. First, we have to initialize a variable received byte. Okay. Now we will in the interrupt, when the received byte it's in the UDR register. We read this received byte, so the next byte could be received. When the register is not empty, we will have a data overrun error in the microcontroller when we are not reading the received byte. what we have to set up, it's an array or a string of values where will be all the information from the GPS sensor. And it will have the length of, for example, 20 characters. Okay. Now I will try you to use the GPS for receiving some characters. Okay, now I will turn off the camera. Okay. And now I will search for the serial interface which I had connected to the computer. It's an USB serial converter. And you are launching the device manager and see which is our USB to serial port. It's COM7. So I will start then. I will choose the COM7 and launch the serial port monitor. And now I will connect the GPS receiver. Hopefully it will work. Okay, this is data from our GPS receiver. Okay, I will disconnect it only to see the data format. Okay. For our purpose, it's enough to read the RMC sentence. These sentences are from the NMEA standard, and this is a recommended minimum sentence for the GPS. So this is, for example, 8:41. It's GMT time. So now it's 8 o'clock in the morning and 41 minutes and 4 seconds. This A means that the data are valid. This is the latitude and longitude of my GPS receiver. This is the my speed. It's 0.4. It's only a noise because the GPS receiver is not moving. And this is the date. It's 30th of November 21. This is the checksum. So we have to read this GNRMC sentence. I will copy the sentence which we have to read as a comment to our code. For processing it. Okay. I will delete this previous example. And what we have to set up is to receive these bytes as an information about minute, hours, minute, and seconds. Okay. So, what is the first character which is the beginning of the sentence?
I don't know.
The first character is this $sign. So we have to search in the received string for $. So if received byte is $, we have to set up a new variable. The array index will pointing or an array pointer will point to the position in the array or the string. Array index will be 0. Next, we have to fill the received string with the received values and increment the array index. And we have a limitation that we are receiving only the first 20 characters. So we have to make it in a condition Sorry. Okay, I will switch on the camera for you for the, okay, it's automatic. Okay. We are filling the string with the bytes. Okay, then we have to check if there is if the sentence received it's an GNRMC sentence or not, because the GPS receiver gives you more information. For example, the GPGSV, it's the satellites in view, or GLGSV, it's our GLONASS satellites in view, and so on. And we don't need this information. We want only the information from the time. Okay, this character, the $, is 0. This G is 1, N it's 2, R it's 3, M it's 4, and C is 5. This is the index of these characters in the string. So we have to wait for loading these characters from the sentence and to check if there is the RMC. How we will make it? We set up, for example, a new variable. RMC presence. It will be 0 initially. And we have to check there is an RMC in the received string or not. The first, we have to wait for filling this first five characters. For example, array index, it's more than 5. And the third character in the received string, third character is R. The fourth character is M, and the fifth character is, okay, this is failure. Is RMC. Okay. So this is the condition if the array index is more than 5 and the received string is the R on the 3rd position, the M on the 4th position, and the C on the 5th position. If it's true, the RMC presence will be 1. When it's not true, for another type of sentences, the RMC presence will be 0. So we are not reading the wrong sentence. It's important. Okay. Now I will display on the okay, I can delete it. The first number I will make for the RMC presence, and I will see if there is received G and RMC sentence. Okay. Okay. Okay, I will connect the GPS receiver. Do you see that there is flashing 1 in the last position?
Not really. We can't see very much. Oh, yes, I can see it.
It's very fast because the sentences are sending in the... Okay, I will disconnect the GPS receiver. Okay, so this is working. Okay, now we have to program the clock. The clock is already programmed from the some of our exercises, and the first digit was minutes. Minutes. Hours divided by modulo Okay. Okay, how we will receive the information from the GNRMC sentence to our minutes and hours. If presence is 1, then we have to load the minutes, seconds, and hours to our information about the time. So first we could load the seconds. The dollar is 0. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10, 11, and 12. The seconds. 5, 6, 7, 8, 9, 10, 11, 12. Is the received string. Okay, fine. The received string 12 subtracted by so. Okay, what I'm doing here. This is the received string 12. The received string 12 is the second the information about the seconds from the GPS receiver. But it's in an ASCII format. When you looked in the ASCII table, you will see that the character 0 has the ASCII value of 48. But I'm not, and the other numbers have, for example, 1 is 49, 2 it's 50 in the ASCII table. But I'm not remembering what is the exact number of the 0, so I will use this notation to force the translator to put the ASCII value for this 0. Okay, I will make the same for the minutes. But the minutes are in this area. So this is 5, 6, 7, 8, 9, and 10. So it's 10, 9. And the same for hours. But the hours are here. So this is 5, 6, 7, 8. Okay, but this is not the all condition. These data are not valid when this is another letter. The A means that the receiver has received all the information from the satellites. So I have to check if this A is if on this position is an A. So this is 0. This is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So received string in the 17th position, A. If this is so, I could read the information from the GPS receiver and put it as a time on the display. Okay. Let's try to build this. Okay. Okay. So this is not the correct time, but now I try to connect the GPS receiver. And now it's 9 o'clock and 5 minutes. Is it okay or not?
Yes, it is.
Yes, because it's Greenwich Mean Time, GMT. So UTC plus 0, the English time. But in France, it's the same time zone as in Slovakia, not?
Yes, it's the same one.
Yes. So we are not using the English time, and we have to add time zone information. And we have to zone is 1. And this is not the end. Because we have to make the dividing modulo by 24. Why? This is because when you have, for example, higher time zone, for example, like in Finland, +2, or like in Russia, +3, you will recognize that in when it's midnight, it will show you 25, 26, 27 o'clock. And then it will change instantly to the 2 or 3 in the morning. And it's not correct. The clock, the hour information, it's only from 0 to 23. Okay. So this is the information, and now it's 10 o'clock and 8 minutes. The GPS receiver, it's an GPS receiver module. It's possible to buy it on, for example, AliExpress, for example, for $5. And it's very simple to integrate with microcontroller. You are connected to Arduino only 5 volts to supply the GPS. The TX transmit wire from the GPS to the RX of the microcontroller, and ground of the GPS, and it's everything. It's okay.
Okay.
Okay, but
Yes.
now I see that the time it's not incrementing, so I have the failure. Here, when the time is not changing. So I have commented the timer 1, which is a timer for each second. Okay. And now when I program the Arduino, now when I connect the wire from the GPS to the Arduino, so now it's 10 o'clock and 11 minutes. And when now it's uncommented, you will see that it will change to 12 minutes.
Tak si puszczaj, że nie tak ci go to już. No.
Okay, or probably not. Okay. Now there is a failure in the code, and so this we should do only in the only in the interrupt.
Počkaj, pôjdeme von za chvíľu. Chodíš tam. Makaj, choď, máte tu si Lala? Lala, ideš pozerať Lala?
Tam Hala.
Nie, Halal robí úcko, tuto robí Halal. Ty musíš ísť do obývačky. Poďme ona.
Sorry. The time zone is declared in the main function. It has to be declared before. Okay. Okay. Now when I connect the GPS receiver to the Arduino, it should increment the time by its own. Okay, it works. Now it's synchronized. The clock is not it's not synchronizing every second with the GPS. When you are making your own project, including GPS, you could, for example, set that the GPS receiver it's synchronizing, for example, every hour or every day. You should turn it, for example, for 5 minutes in a day. When you received a complete sentence, including A, it's a valid sentence. Then you synchronize the clock, hours, minutes, seconds, and then you could turn off the GPS receiver. Because it's not very important to have, for example, 0.2 second accuracy for the clock. Okay, do you have some questions?
No, I think it's okay.
It's okay. I will share this code to the teams so you could see it.
Oh yes, please.
Okay.
And is it possible that you can also, I don't know, send us the data sheet or few codes that we already did? This way we can review it for the exam.
The data sheet for Atmel 328P, the Arduino, you could find on the internet.
Okay.
It's this device, ATmega 328P. It's the same chip that on Arduino. This one.
Okay.
And it's easy to find on the internet. Or when you have the Microchip Studio, you click on the device, and you click on the datasheet, and there it is.
All right. Thank you.
Okay, you're welcome. Okay, see you next time.
See you.
Bye.
Bye.
Ko sa s ním zahrát na kuku ty rybičky.